It made it disappear before, so let's pull it out again. He's okay. He's all right. All right. Okay. So here we go. This is the region you were working on. So here's the functions, and so it's tempting to want to say this is the region where I put the arrow. But what's wrong with that? That uses the y-axis, or x equals 0, and that's not one of our three. So there's only one region, which is this one, that's only bounded by those three. So don't assume that one of the axes are going to form your region. In this case, it doesn't. So we've got this kind of triangular region with a little curved edge there, curved hypotenuse. Okay? And we're going to rotate around y equals 1. So let's make that stand out. All right, and so we're going to rotate, and then let's show it here. Okay, so we want that region rotated around y equals 1. So if we were to do that, so let's find these points. These points are going to be helpful. So let's find these points. This has x coordinate 2 and y coordinate of. So if you do the math, right? So how do you know that it's y coordinate of 3? Well, it's the y coordinate of your curve when x equals 2. So if you plug 2 into that quadratic function there, where am I here? So if you plug 2 into the curve, oh, I wonder. Okay, we're back. You get 3. So what about this point? That's easy. That's just the intersection of these two lines. It has to be 2, 6. And then? So now this is going to be what? It's going to be the x-coordinate when y equals 6 in that curve. So you plug y equals 6 here, solve for the x, and you get the 4. So you get 4, 6. All right, so 2, 3. So when 2, 3 is rotated about the line y equals 1, where does it end up? 2, negative 2. Is that right? So 3 is how far away from 1? That's 2 units. So now we're going to go 2 units down. Is that negative 2? It should be negative 1. But that was the right idea. That was the right idea. So that point, when we get halfway around in our rotation or revolution, it's going to be there. Where will this point be? So we're how far away from 1? 5, right? So from y equals 1, go down 5. And you get 2? Negative 4. So this is, what, 1, negative 4. This point also. Thank you. Yep, 2, negative 4. Thank you. And this is 4, negative 4. I know I said the art doesn't matter, but it matters to me. Oh man, that's terrible. Down big. Oh, and then I didn't use blue. Okay, here we go. So that's what it'll look like when it gets halfway around. So you're gonna imagine if you take that perimeter all the way around, what empty shell do you get? What empty shell you get? And so let's see if I can do that fast. Something like this. Is that something like that? So it's kind of like a weird roll of toilet paper. Okay, and so the shell, that we're filling up is if we turned it up, then like water could go right through that, right? So the shell that we're going to fill up is the outer part, right? Would be this part is the shell that we're going to fill up. Okay, so first, any questions about the region or the empty shell? Let me get this proportions a little bit better here. Okay, that's a little bit better. All right. Okay. Questions about the region or the empty shell? So now we're going to use delta x intervals. So even though we didn't like hold your hand and tell you draw the delta x intervals and draw one cylinder, you still should do that. We said all that because it's really helpful. So we want to think about these delta x intervals this way. And then in the current interval, so we're imagining what these cylinders are filling up. These cylinders are being generated through delta x intervals. And the current cylinder, we'll do it in red up here, is going to be what kind of cylinder? So it's going to be a right cylinder, and it's going to be one of these. So it's great having all the really fancy animations, but there has to come a point where we have to imagine it and sketch it ourselves. So these are going to be, when we do delta x intervals, these are what the right cylinders are going to look like. And so then the first question we ask, as x increases through these delta x intervals, what's changing of these cylinders? The current cylinder, does the height change or the radius change? What's changing? You should be thinking the height is changing. So the height is dx in the current interval, right? We have these delta x intervals, and the current interval is where the current cylinder is being generated. Its height is dx, and that's what's changing, the height. Therefore, the rate is? When the height of these right cylinders changes in the current interval, the rate is pi r outer squared minus pi r inner squared, right? Area of the base. Area of the base when your height changes. Is that what we said last week? The rate of change is the area of the base, and this now the base is turned up vertically, right? So you got to see that the height is now horizontal and the base is vertical. Okay? So r outer minus r inner. So first r outer. And remember, so we got to figure out what is this radius. And so it's from our axis of rotation up to the outer radius here. And so we ask the question, is that an x coordinate, a y coordinate, a big change in x, or a big change in y? X coordinate, y coordinate, big change in x, or big change in y? Remember, this is y equals 1. Is it the y coordinate? It's not the y coordinate because we're not revolving this thing around the x-axis anymore. We're revolving it around y equals 1. So it's not a y coordinate, but it is some big change in y, right? It's the change in y from y equals 1 out to the top of, or out to the far radius of our cylinder. So what is that big change in y? 5. All of them are bounded out here by y equals 6. So it would be y equals 6 minus 1 is r outer is 5. Okay, what about the inner radius? The inner radius is from here to here. X coordinate, y coordinate, big change in x or big change in y. It's another big change in y. It's not the y coordinate because, again, we're revolving around y equals 1 now. Okay, so what is that radius right there? The inner radius is? So it's going to be that y value, but minus, right? So it's like y final minus y initial. A big change in y means y final minus y initial. Y final is the y coordinate of our curve, which is 1/4 x squared plus 2. That's y final minus 1 is y initial. There's our big change in y. That is our inner radius of this right cylinder. So we're ready to, we got the rate of change now. We just plug R0 is 5, Ri is this. And what is our independent variable? X is our independent variable. We've got delta x intervals, and we're letting x increase through delta x intervals. So x is our independent variable. So we need to write, is everything in terms of x then? All our radii? R0, 5, that's fine. Ri is in terms of x. We're ready to write the volume function. So this is, call it volume number 1 in terms of x. How do we write it? Is this total accumulation or net accumulation? Yeah, we want total. So V1 of 0. Is that right? V1 of 2, right? So we're starting at 2. Then, see if you can finish it. Take 30 seconds. See if you haven't done this yet. Finish the volume function. Should be able to do this. Is it right? It's not right, okay? But, so what do I need to do? I need to use t's, right? Or some other, I could use u, whatever, some other letter. I can't use x because x is how far we've accumulated to, right? T has to be every x value between the starting x and x that we're accumulating to, okay? Okay, any questions on that? Yes, sir. Yeah, so if we were to specify the domain of this, it would only make sense up to 4. That's right. So, yeah, we usually don't, but that's okay. Yeah, so you say 2 less than x less than 4. Other questions? Okay, so can you draw? So now in delta y intervals, can you sketch one cylinder for delta y in the current? Like if you imagine delta y intervals, first of all, imagine delta y intervals, and then imagine the cylinder being generated in the current delta y interval. Could you sketch that, and could you get the rate function? Go, I finished taking attendance, okay? Looks like this. Here's the shells that are generated through delta y intervals. They look like this when delta y is small. Okay? So as y changes, as this shell is generated, is the height changing or the radius changing? Radius changes. Therefore, the rate is 2 pi rh. Okay, so the radius first. The radius. X coordinate, y coordinate, big change in x, big change in y. Big change in y. Y equals 1 is here. And so what is this y coordinate? So imagine this is this thing right here. So this is a typical shell, right? Typical shell in the current y interval. So it's the y coordinate of what? It's the y coordinate of this curve. Minus y. So this is simply the y coordinate of the curve. So the radius is y minus 1. The height. What's the height? The height is this dimension. X coordinate, y coordinate, big change in x, big change in y. It's a change in x, right? It's this change in x from here to here. This is the height of this current cylinder. It's a change in x. So what is it? It's going to be the x coordinate of this curve minus 2. So the height is x minus 2. So we could start by writing the rate function as 2 pi, radius we said was y minus 1, and the height is x minus 2. What's our independent variable, x or y? Y is the independent variable. So this is perfectly fine. It's just y minus 1. It can stay because it's in terms of y. But this has to be converted to y. So 2 pi, so the rate is 2 pi y minus 1 times, what is x? Y minus 2 times 1/4 square root, right? First subtract 2, then multiply by 4, then take the square root. So it's going to be the square root of 4 times y minus 2 minus 2. Oh, wait. It's not under the square root. Thank you, sorry. That's that minus 2. So there's the rate function. 2 pi times y minus 1 is our radius, which is our change in y. The height is the change in x, which is the x coordinate of the curve, minus this x coordinate is always 2. So there's your rate function. I owe you lots of time, guys. I owe you time.